Hello guys, welcome back to Word Math Circle's Math Counts training. This is session 12 of a 12-part series where we teach you everything you need to know about the MathCounts exam. My name is Mugil. I'm going to be presenting these videos for you guys. Alright, so let's get right into it. So session 12 topics. What exactly are we going to be learning today? Session 12. So today we're covering the following topics: grids, back calculation, and finally a conclusion. And we do have some subtopics that we're going to be learning today. First, some basic knowledge of SAM problems about grids. We are going to be going over some basic ideas and examples for back calculation. And finally, we do have some updates for the MathCounts exam, as well as a conclusion to our course. Okay, so let's get right into today's topics. Okay, so first let's go over grids. Pix Theorem states that the area of a polygon with vertices as lattice points on a unit rectangular grid is area is equal to b over 2 plus I minus 1. Now here, b is the number of lattice points on the boundary. So if you see this figure and the solid black line that denotes this boundary, any lattice points on this boundary, they make up b. I is the number of lattice points inside the polygon without touching the boundary. So all these points in the middle that don't touch the edges, those are going to be your I. So when you just plug in your numbers into this formula, you can find the area. All you really need is a picture or a figure of that polygon that you're trying to find the area of. Now, sometimes polygons will have holes, like the one right up here, or this one too. If you see both these polygons, they have a hole in them, so we need to account for that. And Pix Theorem is not accounting for that, so we need to modify our formula. So for a polygon with n holes, the area is a is equal to b over 2 plus I minus 1. So the same formula, except we're going to add n, so plus n, and this is n holes. So when they say holes here, they're referring to a unit hole, right? So here, it only takes up one unit square here, so this is one hole. So my n is equal to 1. I just plug in 1 here, and I do my formula like usual. Now similarly, a grid can be rectangular, or in this case, triangular. So here we have a rectangular grid, or square grid, you could say, because you can make a square. Here, however, we can make triangles out of 3 points, so this is a triangular grid. So now we have different formulas because it's a triangular grid. So the area is going to be b plus 2I minus 2, right? So similar formula, just a little different, but b and I are still the same thing. And the area with holes is going to be b plus 2I minus 2 plus 2n. And remember, the holes are just going to be unit triangles that are inside the polygon. Okay, so those are the 4 formulas you need to know. Make sure to recognize what type of grid it is so you can use the proper formula, and make sure to identify any holes. But in reality, these formulas are just simple plugging. Okay, so let's go over some lattice points on a triangle. So the number of lattice points on or enclosed by a triangle, so on the boundary or inside the triangle, and the vertices are at 0, 0, m0, and 0n is t. So the number of lattice points is t, where m and n are positive integers. T1 is the number of lattice points inside the triangle, and T2 is the number of boundary points. So the number of lattice points on or enclosed by the triangle is going to be T is equal to T1 plus T2. Pretty simple. We're just breaking this overall T down to T1 and T2, so it's easier to calculate. So to find T, our formula is going to be 1/2 into m plus 1 into n plus 1 plus the GCF of mn plus 1. We went over GCF in the first video of this series. Now T1 is going to be 1/2 into m minus 1 into n minus 1 minus the GCF of mn plus 1. So we have all these minuses here because T1 is only the number of lattice points inside the triangle. It doesn't account for those on the boundary. And T2 here is going to be m plus n plus the greatest common divisor of m. So m plus n plus GCD of m. So if you know what your T1 is and you know what your T2 is, you can find T directly. Or you could just use this formula to find T. So either way, you can use this to find the number of lattice points on or enclosed by a triangle with these vertices. Now, if m and n are relatively prime, right, so they don't share any factors, then T1 is equal to m minus 1 into n minus 1 over 2. So a slight change if they don't share any common factors. But here, again, it's just plugging in your m and n values based on where the vertices are at, and then you can find your answer. Okay, so let's go into lattice points on the circle. This is a similar idea, just a few different formulas. So here, our formula is going to be the number of lattice points on or enclosed by a circle, so similar thing, And this circle is going to be u squared plus v squared is equal to x. So the number of lattice points is going to be r of x. So earlier it was t, now it's r of x. Now r of x is equal to 4s plus 1. And here s is equal to the floor function of x over 1 minus floor function of x over 3 plus floor function of x over 5 and so on until you get to your final answer. So basically here what they're really saying is if you have a circle of this form, right, then you can find how many lattice points are on or enclosed by this circle. And what you basically do is you calculate 4 times s, and s has its own formula, plus 1. And if you see, this is going to keep going on until you get to your x value itself. And you're going to alternate between a plus and a minus, and then the floor function basically finds the greatest integer that is equal to or less than this integer. So here, if my x was 5.1, my floor function would give me a result of 5, right? So based on that, you can calculate it. So an example of this is the circle x squared plus y squared is equal to r squared. So for r between 0 and 10, right? So basically, this was our original formula. Now we're going to modify it for this circle in particular. X squared plus y squared is equal to r squared. So when r is between 0 and 10, so x here is between 0 and 10, the values I get for 4s plus 1 are 1, 5, 13, 29, 49, 81, 113. So as you can see from that, basically it's really just plugging in whatever your r value is into this formula so you can solve here. So it's 4s plus 1, and you know how to calculate s because you just plug in x here. So here, this one's in a weird form, but basically here, r is your x. So basically you're going to be plugging in your values over here. Or I should say square root. But basically, again, you're just plugging in the values into this formula and then doing 4 into this plus 1. Pretty simple. Now, we also do have a formula to calculate lattice points that are on a curve, right? If y is equal to f of x, and this is a strictly increasing function, right? So it's the y value is increasing. The inverse function of y is this y, right? So this is 5y. So the inverse function of y is 5y. Then with f of 0 is equal to 0, and f of a is equal to b, and these are positive numbers, then there are L lattice points in the arc of a curve y is equal to fx from O, so this is O, which is 0, 0, to b, which is AB, and these are coordinates. This is including b, but not O. So it's including the endpoint b, but not the endpoint O. So we'll go over that again. So basically, if you have a function, and you have its inverse function, right, it's a Greek letter in y. So then if you know that f of 0 is equal to 0, and the f of a, so when you put a into this function, you're getting b, and these are all positive numbers, then there are L lattice points in the arc of the curve. Now, what you do is you have one endpoint, which is O, 0, 0, so this is not included. And your other endpoint is going to be AB. Remember, f of a is equal to b, that's how you get your a and your b. So then you can calculate all the L lattice points that are in the arc of this curve until the point b, including b. So the number of lattice points on or enclosed is going to be n is equal to the floor function of a times the floor function of b. So if you know what a and b are, basically you're all set for this formula. You can find the number of lattice points on or enclosed by that arc. Again, floor function means you're going to be finding the integer that is greatest or equal to this number inside the floor function. So here, if I had like a 5.5, then my answer would be 5, right? Because that's how a floor function works. Okay, so once again, here you have your formula for the circle, and you're just plugging in here, right? So here, as you can see, it says u squared plus b squared is equal to x. Here we have x squared plus y squared is equal to r squared. So you can simply make it equal. So x is equal to r squared. Based on that, solve for what your x value would actually be, and just plug into this formula. Okay, so let's go over a sample problem. A polygon is drawn with its vertices on the points of a unit rectangular lattice. There are 6 lattice points on the boundary of the polygon, and 4 in the polygon's interior. How many square units are in the area of the polygon? So here they haven't actually given you an image. However, they've given you all the relevant information you need, all the variables, so you can just plug into your formula. So go ahead, pause the video, and try to solve this one. Okay, so hopefully you pause the video and you try to solve this one. Let's go over the answer. So we can use Pix Theorem to solve this problem, right? There are no holes in this polygon, so Pix Theorem works perfectly fine. So our formula is A is equal to, so area is equal to B over 2 plus I minus 1. Here, our B is equal to 6 and our I is equal to 4. How do we know this? Well, they've given it to us. They said that there's 6 lattice points on the boundary of the polygon, and 4 in the polygon's interior. So we're just plugging in at this point, right? And it's b over 2, so 6 over 2, which is 3. And then I is just 4, so that's 4 minus 1. So that's 3 plus 4, 7. 7 minus 1, which is 6. So our final area is 6 square units. So here, it's just simple plugging in. Sometimes they'll give you an image. Here, they just gave you the numbers itself. All you have to do was plug in. Okay, let's go into our second topic of the day, back calculation. So for some word problems, based on the result given, you can find the desired solution. Sometimes you're given the final result, and you're asked to find what they started with. So here are the basic ideas. If you're solving normally and you use addition to go forward, for example, if you're trying to find the sum of something, then you use subtraction when using back calculation, and vice versa. Similarly, if you arrive at the final result using multiplication, use division when back calculating, and vice versa. So this may seem a little confusing at first, but once we do a few examples, it'll become quite clear what I really mean by using the inverse operation. So we generally use back calculation when we're given the final result, or we cannot solve using normal calculation. Sometimes you're given what they end up with, but you want to find what they started with. We also use this method when the details of each step are known, or when the unknown is the information at the beginning of the problem. So we're trying to solve for the information at the beginning of the problem that just wasn't given. Okay, so let's go over an example. So Augie spent all his money in 5 stores. In each store, he spent $1 more than 1/2 of what he had when he went in. How many dollars did Augie have when he entered the first store? So here, they say that he spent all his money at 5 stores, so he has $0. So they're giving us the final result, but we want to know what he had when he first entered the first store. So for this one, forward calculation won't really work. We have to use back calculation because we're going to go back and try to find the initial money that he had when he first entered the store. So that's why we're going to be using back calculation. And this is from the 1993 National Sprint of MathCounts. So normally we would divide his amount by 2 and subtract 1. That's how we get the final answer, right? At each store, he's going to divide his money by 2 because he's using 1/2, and then he's also going to subtract 1 because he's using $1 more than that. Since we're using back calculation, we're going to add 1 and multiply 2, right? Here we're dividing and subtracting, so we're going to add and multiply. We're just using the inverse operation. So when Augie was losing his money, he was dividing and subtracting. So we're going to use addition and multiplication. So after 5 stores, he has $0. After 4 stores, he's going to have $1 times $2, right? 0 plus 1 is 1. 1 times 2 is going to be $2. After 3 stores, similarly, we'll get $6. After 2 stores, he had $14. And after 1 store, he had $30. So at the start, he had $62. We had $62 at the very beginning of this trip. So normally, sometimes they just give you the $62 and ask how much money does he have to end. But in this case, since we want to find the money he had at the beginning, that's where we're going to use back calculation. And as you can see, it wasn't anything super complicated. It was just a little bit of PEMDAS, and we're just doing it multiple times. So again, what we're really doing here is we're just back calculating by using addition and multiplication instead of division and subtraction. Alright, so let's go into some simple instances of back calculation. Okay, so a number added to 1 equals 10, right? So we want to find the number. So n plus 1 is equal to 10. So we're going to do 10 minus 1 is equal to n. So a number added to 1 equals 10. So basically now we're doing subtraction to find our n. These may seem really simple. They're basically simple linear equations. But basically the point here is we're trying to emphasize how back calculation really works and how you would change it if you were given something like this in a word problem. A number subtracted by 2 equals 8. Find the number. So n minus 2 is equal to 8. 8 plus 2 is equal to n. Here we did subtraction, so we're going to do addition and back calculated. A number times 3 is 24. Find the number. N times 3 is equal to 24, so 24 divided by 3 is equal to n. A number divided by 4 equals 6. Find the number. So we're doing division, we're going to do multiplication when back calculating. N divided by 4 is equal to 6. 6 times 4 is equal to n. Half of this number is 6. Find the number. 1/2 times n is equal to 6. So 6 times 2 is equal to n. 1/3 of this number is 6. Find the number. 1/3 times n is equal to 6. So this really should say 6. 6 times 3 is equal to n. 1 less than half this number is 6. Find the number. Well, 1/2 times n minus 1 is equal to 6. So 6 plus 1 times 2 is equal to n. 2 more than 1/3 this number is 6. Find the number. Well, then 1/3 times n plus 2 is equal to 6. So 6 minus 2 times 3 is equal to n. So really, these were self-explanatory, and you could have thought, well, these are really easy to do. But basically, the whole point here is we're emphasizing how back calculation really works. I'm adding here, so I'm going to use subtraction when trying to find n. Or here, what I'm doing is I'm adding first, right? So that's why I'm going to be doing some subtraction over here to get my n. Basically, you're going to flip the operation when doing back calculation. Always remember that. Okay, so let's go over some problem. So a man said that when my age is increased by 14, divided by 3, decreased by 26, and multiplied by 25, it equals 100. So you're given the final answer, but you want to find his original age, which is what you started with. So you need to use some back calculation here. And they've given you all the operations, so just flip them and you can find his age. And it's from 20 more problem solving skills for MathCounts by Jane Chen. Alright, go ahead, pause the video and try to solve this one. Okay, so hopefully you tried to solve it. Let's go over the solution. So for this problem, we can use back calculation, right? So the first operation we did was multiply by 25. So here we're going to do divided by 25. 100 divided by 25 is 4. Now the next operation we did was subtract 26, decrease by 26. So here we're doing add 26. Then we're going to do times 3 because it was divided by 3 earlier. And then we're going to subtract 14 because earlier it was adding 14. So again, 100 divided by 25 is 4. 4 plus 26 is equal to 30. 30 times 3 is equal to 90. And 90 minus 14 is equal to 76. So using back calculation, we were able to calculate this man's age by simply just performing the inverse of the operation. It wasn't hard. We were just basically flipping each and every operation that was done. So we find that his real age is 76. Okay, so that's all the MathCounts topics that we're going to cover for this course. Obviously, there are some more and like some more esoteric topics that you can cover. So you can go ahead and search up more problems, and you can find these topics that are a little more minor or not as major. But we've covered a majority of the main topics. So there are some updates about the MathCounts exam. So I would encourage you guys to make sure to check out the MathCounts website for helpful resources and practice. They have practice problems every day, and they also have some practice tests on there. So go ahead and check those out. So this year's competitions have actually concluded. But next year they will start again, and hopefully in person as everything goes back to normal. So the practice tests are generally November and December. So November and December of this year, you'll probably get your practice tests if your school is registered. And the actual rounds generally start in January or February. And as you progress and as you do better, you will go on to the chapter sprint and the state sprint and the national sprint and so on. So remember to ask your school to register for these if they haven't already done so. There are many programs that MathCounts offers. Your school can register for them. Just make sure to ask your school if they don't have a club to form one, and make sure to remind your advisor to register for these. Make sure to check all the rules and recent updates on the website, because as of right now, these competitions are going on, but they could be canceled or there could be a date change. Make sure to go out and check it. And here's a helpful link, www.mathcounts.org, competition rules, FAQ. So if you go ahead and check out the MathCounts website in general, you can find lots of helpful resources that will help you. Okay. So let's also go over a little conclusion to our course. So after watching these videos, you now have a strong understanding and foundation of MathCounts topics for the exams. However, do be warned that some of the problems on the MathCounts exam will deal with more advanced problems based on these basics. So while these may be similar to the sim problems that we've always done throughout the course and we've done these SAM problems, they may involve more work or they could be a little more complicated. So we recommend practicing these more advanced problems and buying the books, right? 20 more problem solving skills for MathCounts exam by Jane Chen, or just 20 problem solving skills. There's 2 books, right? One is 20 more and one is just 20. So I'd say go ahead, buy those books or check those out if you want some more practice. She does have much more advanced problems in there. And you can also search up past MathCounts tests online. You can check out the MathCounts website. There's a lot of resources. Your chapter advisor also has some resources. Go ahead, check those out. They're really helpful. And I'd say practice a lot more before you take the exam. We've taught you all the basics, but you want to keep practicing, keep in touch with these concepts before you actually take the exam. So make sure to keep practicing and use what we've taught you. And remember, practice makes perfect. So here's our final statement. Thank you so much for watching this series. Hopefully you really learned a lot. Good luck on your MathCounts exam. I wish you the best on your journey. I hope you guys find success. Thank you just for watching this course. Hopefully you've learned a lot. Please give us any feedback you may have. And good luck in your journey. Good luck in life. Hopefully you succeed on the MathCounts exam and your math journey. Thanks for watching. Please like and subscribe if you enjoyed the video. Leave a comment with any questions you may have. Bye guys.
Don't forget to subscribe and like if you you have any questions, you can email info@agouramathcircle.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end. So bye!